Hello everyone, this is part 4 of the Marconi 6200A microwave radio test set repair. I just thought I'd show you before we go any further into the module specific repairs, looking at them, how we can look at the RF level coming out of the microwave test set. Currently we're in a hidden menu which I've got access to, a diagnostics menu for source diagnostics within the test set, and as we can see in this particular screen, if you look in the top left it says Yig tuning DAC, and then beneath it it says level DAC. Well, that is the control of the ALC, the automatic limiter control for the RF output. And so what happens is when we calibrate the instrument under the calibrations function, we connect a power sensor. This is a scalar one at the moment. Oh no, that's a power sensor. We connect a power sensor like this to the RF output, and that then connects into port D on here, the power sensor. And what happens is we run a special diagnostics procedure that calibrates the instrument from 10 megs to 20 gigahertz in this case. And what happens is the test set outputs an RF level which is decreed by the DAC, which is just here in the top left hand side of the screen, this 65,535 value. Basically that value goes from 0 up to 999,000 whatever it is. Basically that's its entire range, and each instrument has a different value depending on its own individual characteristics. But what it does, it finds that value by, for example, starting, say for example you wanted to calibrate it narrowband from 1 gigahertz to 2 gigahertz, just for argument's sake. It'll output a 1 gigahertz signal at different RF levels, and it knows in itself that if it's going to calibrate, say, a 0 dBm level at 1 gigahertz, it'll then adjust the voltage to the diode attenuator that we were showing in the previous videos, so that it then, this is obviously calibrated first, you calibrate it, so then it'll increase or decrease proportionately the RF output until it gets to 0 dBm read by this sensor. Once it gets to 0 dBm, whatever value this DAC might be, it'll save that then to memory within the test set, and then it'll move on to the next level, and it'll do it in 1 dB steps. And it's quite a lengthy process, but it'll do it from, basically if you're doing it broadband, it can take quite a long time, hours even, for it to do it, because what you do is you have to input the linearity data and all the calibration data into the instrument for the sensor, because they've all got their own linearity data printed on them. You have to input all that in first, calibrate the sensor, go to your calibrations menu, which is password protected by Marconi, start the broadband power measurement, which will do from 10 megahertz to 20 gigahertz. And what it does multiple frequencies, obviously from 10 megs to 20 gigahertz, but it'll measure across its entire dynamic range in 1 dB steps. So it'll go from the absolute minimum value up to the absolute maximum value of the RF output in 1 dB steps. And each 1 dB step, once it's attained that level from the RF output and it's measured it and it knows that that's the DAC value that represents the RF level, it will then save that into memory, into its calibrations memory, and then it'll progress on to the next frequency and do the same again, and it'll do this through the entire frequency range. So as you can understand, it can take quite a long time for that to occur. Now in this particular case we're in the service menu, a hidden menu within the test set that gives us access into the diagnostics functions. And if I do source control, and I think it's the, let's have a look here, there's level DAC, so we'll select that. We've got the value that it currently is, and we can adjust that just to see what happens with the output, because this is a diagnostics menu, not a calibration menu that we're currently in. So what I've done, I've connected the microwave sensor to the Marconi power sensor thing here, this gadget. I don't know about others, but I wish Marconi, when they made these, it had done a backlit display, because they're quite difficult to see in very bright conditions. And so at the moment we've got 19.76 dBm coming out. Now if I adjust that DAC level down, we should be able to see it'll finely control the RF level, and it takes some doing because it's very precise. It's, as you can see, it's dropping to 19.74 now, and I mean I'm whizzing my finger around on this thing. So if I input a value, say 65,244 at the moment, let's just put all the 5s in, 5555, and then enter. There you are, look. So it's dropped down. If we put all the 4s in, 4444, enter, and it drops again. Oh, changes. Let's do all the 1s. There we are. It's gone right down to that level. All the 2s, enter. So you can see that's how it can control the level. So by adjusting this level, which obviously is very finely adjusted, it can get a precise level output recorded within its own memory and then progress throughout the frequency range. Now it obviously does that by sensing what's coming back as per this calibrations routine by using this power sensor, and it does it itself in like a loop mode. Obviously that calibration is only as good as the calibration that's on the power sensor, so you know it's very important that the calibration data which is held within on the sensor is obviously inputted within the menu, the calibration side of things. So that's what I do before I do any calibration. So this this data which is found on the outside of the sensor is what's used to input that at these frequencies. Obviously they're calibrated at 50 megahertz from the calibration port on the front of the power reference port, but then we input all this data in, and on some sensors it's rather than a graph like that, it's shown as a proper table of levels as opposed to a graph. And then we've got the linearity factor which has to be entered in, and then we've got the cal factor. So we enter all these 3 pieces of data into the Marconi test set when we're actually dealing with the power measurement. Now as well as that, there's lots of other diagnostics menus on there as well, so it's quite interesting what you can do with it. But there's a lot of advanced features, and as well as that you can also do the step attenuator as well from here and adjust that. So that's just a little rundown on the diagnostics function which I use to do fault diagnosis. Just to give you a bit of an idea as to the data that needs to be entered in, we've got this table here, and this is a sort of information that you would enter in on the instrument, the frequency, the calibration factor. Then we've got the what is the reference calibration factor is 100%, linearity factor there is 10%. So different sensors have different data because they're all unique, you see, they're all unique. So this is a calibration factor of 6.5, and 90.05% reference cal factor plus whatever's in the table, and then here we've got again different kind of linearity and calibration factor. So that's why you mustn't ever overlook not calibrating first before you do not just measurements but calibrations. You need to calibrate sensors and enter the data into the test set before you use them anyway. So that's a lesson in microwave measurements generally across all radio test sets, be it you know, using a power sensor like this. It has its own calibration features, a Marconi, a Hewlett-Packard, Roden Schwartz, they all do have the same model where you have to calibrate the sensors before you can use them. As well as that, we've got band select mode. We can select it, we can test the pin diode switch here on this menu, which is in the top right hand corner of a display, and that deals primarily with this switch here for the band select. And then on top of that we have other functions as well. We've got RF path switch, we've got source control, which we've just been in, the YIG information about the YIG locks, so we can test the actual locking of the YIGs separately. And then we have the step attenuator option as well, which we can test using this menu here. These are the pads you can switch in and out when the step attenuator's on. They're greyed out on this particular test set because this one doesn't have a step attenuator in it, but the test set that I'm currently repairing does have a step attenuator in it, and they're highlighted when you're in the service menu on that test set. And so this is the step attenuator module. You'll find these in most radio test sets, don't matter whether Marconi, HP, Agilent or Roden Schwartz, they all use this type of mechanical switched pad attenuator that switches in different attenuation pads. So that's just a little rundown on the diagnostics menu. So obviously, you know, when the RF output is coming out of this connector, there's a loop back, a sniffer, a sensor that sniffs back the RF, rectifies it into what appears to be a DC level, and then what it does then is it feeds that back into an ALC circuit, which is compared against a reference, which is obviously what's stored in the level DAC here in memory for that particular power level, for that particular frequency. And then what happens then is that it's like a phase lock loop. It keeps itself locked in a loop, and whenever that level's there, it'll maintain a constant lock loop of RF output. The moment we change the level by altering the variable control here or manually inputting an RF level at a specific RF frequency, it will then recall its memory for that level and that frequency, which was from the calibrations menu, and then it will apply that and then adjust the RF attenuator respectively so that it gives the correct RF output for that frequency. So obviously if you didn't calibrate the instrument properly, it would be like when you obviously use it as a scaler mode and you have the sensor connected on the RF output to the scaler, and you're sweeping from 10 megahertz say to 20 gigahertz, instead of it being a nice flat line like you've got there at the bottom, which you can just see, it should look something like that. It will be like a plateau of mountains. It'll be going up and down all over the place because it can't keep the level in lock, and at different frequencies the level will be higher than others because of the way that the RF circuits perform at those different frequencies, so it'll be all over the place and out of calibration. So join me in the next part when we go further into the more specific fault on this particular test set and do some diagnostics and some testing. So fun times lay ahead. So stay tuned for the next part. Thank you. See you next time.